Okay, then. So it's 6 o'clock. Let's begin. Dr. Gagliuffi she has been here for quite some time, and everybody who's here in the audience, thank you so much for coming and for being patient for some people who have been here and we're just hitting a stock. Thank you for coming again, and I'll introduce Dr. Gagliuffi first. She's an astrophysicist from Peru. Now she's working at the American Museum of Natural History in New York. And before she joined AMNH, she finished her bachelor's in physics from MIT. And then she went to University of California, San Diego to get a PhD in physics as well. And now her research focuses on understanding the formation and evolution of giant planets and round dwarfs through their orbital dynamics and atmospheric composition. So, and yes, we also have our student moderator, who is a very, very excited economics senior undergrad student. Senior, right? I still get those terms wrong. She's a fourth-year student. So, and she is a major in political science and economics. And she was very, very excited. As soon as I said that we have an astrophysicist coming in, she's like, I'm a huge Neil deGrasse Tyson fan, and I need to be talking to this professor who's coming in. So thank you, both of you, especially Dr. Gagliuffi, for waking up super early in the morning. She was still having her coffee when we bombarded her, and she's like, oh, thank you so much for coming here. Okay, so I will hand it over to our speaker, and then Mahnoor will take it over from there. If you have any questions, you can put them in the chat while she's talking, but we will come to the questions, if that's all right. We will come to the questions all together at the end, and the talk will be around 40 to 45 minutes. Okay, then. Thank you so much. All yours.
Thank you so much. Thank you so much, Amna and Mahnoor. Thank you so much for the invitation. I'm really excited to be here. And as you mentioned, my name is Daniella Bardalez Gagliuffi. I am a postdoc at the American Museum of Natural History in New York City. And today I'll be talking about my research, specifically how we can reconstruct planet formation using dynamical and chemical fossils. So most of the stars that we see at night host at least one planet in a huge diversity of planetary systems, but not a single one of these looks like our own solar system. So maybe our telescopes need to become more powerful. Maybe we really are unique in this universe. But something we still don't understand quantitatively, observationally, maybe even theoretically, is how do all of these systems form? What formation pathway can produce this wide variety of systems? And one thing we need to know is that the formation of planets is a consequence of the formation of stars. So we need to study both of these processes in tandem. In the canonical picture of star formation and planet formation, stars are born in a molecular cloud, which is a reservoir of high density gas and dust in space. This is a simulation of a molecular cloud undergoing collapse. And then when material reaches a critical density, it collapses onto itself by its own gravity. So every one of those little dots that you see popping out of this cloud is a newborn star. And as the video goes on, you'll see more and more of these dots popping up. Up in the right-hand corner is the time. So this is a molecular cloud that's making stars from the high density gas. And then as the star begins to spin and differentiate itself from the cloud, there's a disk around the equator that starts to form. It's the same process by which a ball of dough flattens into a pizza. It's angular momentum conservation. And planets then form in this disk, which is also made of gas and dust as the star. But because the disk cools down as time goes on, small rocks start forming in the disk, and this is how planets are formed. So you may wonder now if, since these two processes produce the huge diversity of systems that I presented earlier, you may wonder, what are the limits of these pathways? What kind of objects do they produce? What is the minimum mass for a star? And what is the maximum mass for a planet? Or do these two processes overlap in the products that they can make? So one big difference between these two processes is that star formation happens top down. So I'm borrowing some terminology from galaxy formation, but what top-down means is that we start from general to specific. So we start with a vast collection of material that then produces a star, because the cloud itself cannot hold, it can't hold itself against its own gravity anymore. Whereas planet formation occurs in a bottom-up manner, where the seeds to produce a planet are these small rocks. And as the disk cools off, the rocks coalesce onto a big core that's a few times more massive than Earth. And then that core on its orbit around the star will start collecting gas. And this is how we think Jupiter was formed. Since planets are always associated to stars, the key is to study systems, not just the objects by themselves. And as you will see by the end of my talk, my goal is to identify dynamical parameters and chemical markers that could distinguish between different formation mechanisms. And we'll see that this is more of a continuum than a clear cut across masses. So by characterizing the dynamical fossils left in the architectures of all sorts of systems and the chemical compositions of the stars and planets that compose them, we'll be able to build a probabilistic model of formation, of how all these objects form, identify spectroscopic signatures of formation based on our classification of the formation pathways, and finally, build a chemical map of the galaxy that will allow us to understand the structure and evolution. So again, the key is to study systems, but not just planetary systems. Many stars are born with companions in stellar families of binary and triple systems and more. So in this video, I'm showing only a subset of all of the binary systems that are within a volume of 160 light years with the sun at the center. In fact, the full volume has about 1 million binary systems, but if I had plotted all of those here, then you would just see white the entire screen. It would be very hard to distinguish them. And the sun is a single star, but it had some of a 50-50 chance of being in a companion. So there's a huge diversity, again, in the configuration and makeup of stellar and planetary systems, where essentially all combinations are possible, but each one tells a unique story of how it formed and evolved. So first, let's look at the components of these systems. Both planets and stars can be companions to stars. But about 30 years ago, we discovered a new object that changed our perceptions of stars and planets forever. These are brown dwarfs, and they are the missing link between stars and planets. They're intermediate in terms of their physical properties. So they are less massive than stars, but they overlap in mass with planets. And they're also colder than stars, but they overlap in temperature with planets. The coldest brown dwarf that we know of is about 250 Kelvin, which is, it's about colder than it is outside right now in New York City, but it's a whole star, so that's surprising. And the special characteristic about brown dwarfs is that they cannot fuse hydrogen the way that stars do. So stars fuse hydrogen in their cores. This reaction releases photons, and the photons push radially outwards, and then the upper layers of the star from gravity push radially inwards, and that balance of forces is what keeps a star stable and emitting light throughout its life. But if a star is born with 8% of the mass of the sun or less, which is about 80 Jupiter masses, then its core won't have the required pressure and temperature conditions in order to ignite hydrogen fusion. So then gravity wins up to a certain point. Actually, gravity wins up to the size of, to compress the object up to the size of Jupiter. And that means that the inside can no longer be supported by thermal pressure, but it has to be supported by, this is a quantum mechanical effect called electron degeneracy pressure. And all it means is that atoms are just like pushed against each other. The electrons are like touching each other. This is so compressed that it becomes really, really dense. And in the core, the conditions to generate, to start to fuse deuterium, which is an isotope of hydrogen, are met. However, deuterium is not as abundant as hydrogen, so we don't start a whole new main sequence of burning deuterium. The deuterium burning only happens for a short period of time in the life of a brown dwarf. And then if the brown dwarf is born with less than 1% of the solar mass, or about 13 Jupiter masses, it won't even have sufficient mass to fuse the Theorem or anything at all. And this is our current nominal divide between brown dwarfs and planets. Even though, as you can see, they are actually pretty similar on the inside, and they're pretty similar on the outside as well. So this nominal difference based on mass does not have any physical significance, whereas formation pathway does provide a fundamental definition. We see these three types of objects in all sorts of different combinations. We call these binary systems when you have a star and a star, or a star and a brown dwarf. So we essentially are thinking that the system is defined by the more massive object. And however, we break our rules for planets because they're so special. And so, and systems like this, where you have a star and a planet, we call them planetary systems. But then what do you call something like this? Turns out we also call it a binary system. And I think that reflects our notion that we think of brown dwarfs as a special case of stars. But then we enter this regime where definitions are problematic. So what would you call this? Do we call this a planetary system because it's based on the planet? And for the sake of completeness, what would you call this thing? So we better come up with a solution, because we see all of these systems in nature. But where do they come from and what are their origin stories is still something that we're trying to understand. For example, there's this system called 1207. It was the 1207b, the lowest component here, was the first directly imaged planet. But one thing you should know about protoplanetary disks, where planets are formed, is that their mass is proportional to the stellar mass. So for a more massive star, you have a more massive disk. But in this case, the primary in the system is only a 33 Jupiter mass brown dwarf, which is about 3% as massive as our sun, yet its planet is located 55 AUs away. AU is an astronomical unit, this is the distance between the Earth and the sun. And so this is relative to the solar system, is like where Uranus is. So it's very unclear how there was ever enough mass in this protoplanetary disk in order to form a planet that far away. Another example I have is 1119. It's a system of twins. Each object has a mass of only about 4 times the mass of Jupiter, and they're separated by 6 times the distance between the sun and the Earth. And they both have planetary masses, but they're the same mass. So neither of them could have formed in the disk of the other. And finally, there's the system BD plus 60. It's a system with a solar type primary. So it's a star that's pretty similar to the sun. And its 15 Jupiter mass companion is separated by 16,000 AUs. So again, this formation is very unlikely. This is much, much farther away. The Neptune, which is the farthest planet in our solar system, is at like 40 AUs. So then the question I want to pose to all of you is, do binary systems form any different than planetary systems? And where is that difference? These two parameters that I've been talking about, the relative difference in masses and the separation between the two components, are critical to understand how the systems formed, because they hint at whether formation in a disk was plausible or not. So open questions in astrophysics that I'm hoping to answer with my research are, when does binary formation start to look like planet formation? Can we use dynamical and chemical signatures to understand the dominant formation pathways of exoplanets? And can we answer this question statistically by analyzing populations? Throughout my career, I have approached answering these questions from different angles and using different observational computational techniques. And I've always focused on the interrelation between the objects. And today I'm only going to focus on a few topics, but feel free to ask any questions about any of the other topics at the end of the talk. So now that we've gone over the problem, let's start talking about solutions. Let's analyze these two parameters a bit more closely, the relative difference in masses and the separation between the components in a system. So let me walk you through this plot. First, on the x-axis, we have projected separation. That is the separation that we can measure from the sky. It's the separation between the two components in a system, but projected onto the sky. That's what we can observe. On the left side of this plot, over here, these are systems that are very closely separated. And then on the right side are systems that are whose components are very far from each other. And then on the y-axis, we have mass ratio. It is spelled out here, is mass of the secondary over mass of the primary. This is how we represent the relative difference in masses between the primary and the secondary. So mass ratios, as I said, is simply M2 over M1. A mass ratio of 1 is a system that has two components that have the same mass, and a mass ratio that is very small has very different masses, like the sun and the earth, for example. And both of these axes are in log scale, which means that when we move a little bit to the right or up and down, we're actually moving in orders of magnitude. And every point in this plot corresponds to a system of two objects, with the primary always coming from the star formation process. That means that there's some Brandorf systems here as well. And the colors, and I've color coded all of these points based on the mass of the companion, assuming our current definition of strict masses, strict mass cutoffs for the hydrogen and deuterium burning limits. And as you can see, the plot is a bit of a mess. So here also the three systems that I talked about earlier. 1207, the first directly imaged planet, very much hanging out up here with all of the stars, very far from the planet population. Then there's 1119, the planet-planet binary, quote unquote, and that is very well within the brown dwarf stellar binary territory. It's up here. And finally, BD plus 60, the star with the companion at the deuterium burning limit, is in no man's land. It's hanging out alone here at the edge of everything that we know. These three systems have companions of all similar masses, yet as systems, they occupy different places in the parameter space, which means that there are intrinsic differences between all of these systems that are not reflected by our current definitions of just a companion. So let's take a step back, get rid of these labels that are clouding the physics. At the end of the day, regardless of their name, all of these are two-body systems. They're all bound by gravity. And what is evident from this plot is that there are two main families of companions. In this area, everything formed like a planet from a disk. And in this other area, everything formed like a star in a molecular cloud. So the question is, where does binary formation begin to look like planetary formation? This low density valley in the middle could be the tail ends of two main processes, or it could be a different formation mechanism. But there's no reason to believe that either formation mechanism stops cold turkey at a given mass. So again, there are these two fundamentally different formation pathways that produce two different kinds of objects. The top-down process is called graviturbulent fragmentation, and the bottom-up process, we call it co-accretion. And these two different formation mechanisms produce different objects with different initial entropies, initial internal energies, luminosities, internal structure, and compositions. And they very likely overlap in masses in terms of their products. And some scientists have proposed a third formation pathway for this valley, where very massive disks fragment as a scaled-down version of star formation, but in a disk. And so depending on the disk mass, the pathway could produce objects below or above the deuterium burning limit. So in principle, we could be producing brown dwarfs or planets in a disk. But disk fragmentation requires very specific disk conditions, very specific temperatures, densities, turbulence, and viscosities for this fragmentation to occur, which means that which means that they can only produce a relatively narrow range of object properties. So before we delve deeply into interpreting the yields from each formation mechanism from this plot, we do need to fix a couple of problems. First, we need to carefully map this parameter space to understand where each detection technique works, because we need to understand their completeness, which is with each one of our surveys. And second, many planet masses are only minimum masses because of projection effects, and many brown dwarf masses are model dependent. So the masses for many of these companions here are somewhat uncertain. So let's talk about the first problem. Each companion detection technique is sensitive to a region of this parameter space. We're using a multitude of observational techniques to discover low mass companions to stars and brown dwarfs. But each detection technique is best suited to identify systems in unique parts of this parameter space. For example, radial velocity is a technique in which we obtain spectra from a star, and we see that the spectrum, by the Doppler effect, shifts in velocity back and forth. And the reason is because the star has a hidden companion that is tugging on its, that is gravitationally tugging the star. And so it doesn't stay in place, but its velocity to us and towards us and away from us changes over time. And it looks like this. This is a radial velocity data from a star that I'm going to talk about in a minute. The x-axis is time, the y-axis is radial velocity. And as you can see, there's this like regular period that goes up and down because the star is moving towards and away from us. And this technique is most successful at identifying companions that are closely separated, where this tugging effect is greatest, which is shown by the plot, and all the green points are companions identified through this technique. There's another technique called astrometry, where we measure very precisely the change in position in a star due to the gravitational pull of a companion as well. So this time, instead of measuring spectra, we're measuring the position of the star in images. And this technique is very resource expensive to carry out because it requires extreme positional precision. And it's the reason why there's only 3 companions that have been identified this way. But starting this summer, Gaia, which is a space telescope that has been observing stars for maybe like 5 years or maybe 8 years now, will detect about 60 million binaries with periods between 0.03 and 30 years. So it's going to be a complete game changer. This plot is going to be covered in yellow. And the best part is that Gaia is a population mission. So we'll know the selection function of the astrometry very well as well, and we can constrain masses with astrometry. The really exciting thing about Gaia has already been a game changer in astronomy. It has measured the distances to about 1.7 billion stars and to a really, really high precision. So I'm really excited to see what's going to come out of this now. And then there's direct imaging, which is best at identifying companions that are farther away from their star, but bright on their own. So what's interesting in this plot is that we see that the imaging discoveries kind of span this valley, but this is why selection functions are so important. In order to understand whether we have actually covered the entire parameter space with our surveys, we need to understand how our surveys worked and what were our objectives observing these targets. And that's what a selection function means. It means that I know ahead of time, before my survey starts, what parameter space I'm going to sample. Imaging reaches a resolution limit at very small angular separations and at large differences in brightness between the 2 components. Here I'm showing this example this is the HR8799 system. This is a real video of real data. So I think that's really impressive. There is a little circle here blocking the light from the stars, so we can see the light that's directly coming from the planets. But these planets are fairly far away from the star, which is the only reason why we can detect them, and they're really bright. So that's how we can see them. So the problem is that if the planets were very close to the star, then the difference in brightness would be really high, and the separation in angular space would be very small, making imaging not an ideal way to identify these companions. And for brown dwarfs, that is the big problem, because the brown dwarfs are faint themselves to begin with. So for this reason, I developed a separation independent technique to identify hidden companions through their peculiar near-infrared spectrum. So this is how it works. When 2 objects are closely separated in angular space, your telescope may recognize them only as a single source of light. Like imagine a car with the 2 headlights, but it's very far away, it may look like just one light. And we see peculiarities in the blended light spectrum shown in black. So this is a spectrum right here. I'll take a second. On the x-axis, this is wavelength. On the y-axis is intensity of light. And as the light from the blended system comes through my spectrograph, we split it into its component wavelengths, and it looks like this black line. And the black line looks very peculiar to anybody who has looked at spectra before. So my technique the technique that I designed measured spectral indices, which are ratios of flux of little columns of flux. We take the ratio of 2 columns of flux in order to identify peculiarities in this black spectrum. And then we model the binary spectra with binary templates. So we find spectra for the red object and for the blue object, add them together, compare them to the black line, and then determine whether that's a better fit than just comparing it to a single object. And through this technique, we have identified about 70 candidates, of which about 15 are confirmed binaries, and many more are in ongoing follow-up programs. This produces candidates. So we do go after them with high-resolution imaging, radial velocity, and astrometric variability in order to confirm that these are indeed binary systems. And we have been very successful with this technique so far. But a spectrum is the fingerprint of an object. So there's a lot more than we can learn about atmospheres and scrutinizing spectra. In fact, we just recently learned why some of our spectral binary candidates did not turn out to be binaries after high resolution follow-up. And this is because they have variable atmospheres. So what that means is that these worlds of clouds, like an Earth, and as the object rotates, these clouds come in and out of our line of sight. And the clouds block light from lower layers. So then that results in a change of flux over time. What was surprising is to see that we also find signatures of this dynamical atmospheric process in the spectra, in the static spectra of these objects. By static, what I mean is that you take your telescope, you look at the object for like an hour, and that is your only data point, and that describes most of the object. So this is how we have taken spectra forever, and we have a lot of archival data. But it turns out that we can see some of these signatures that are, and it's a similar process as the spectral binaries, but from a different source. So we figured that blended light could be coming from 2 different atmospheric layers from the same object, as long as the top layer was kind of patchy. So it would let light through from the bottom layer. Or that the object had zonal bands, like in Jupiter. So you may have seen pictures of Jupiter. I think you can see it up here, that have essentially like bands that are created by the turbulence of its atmosphere. So this means that we can learn about a dynamic process from the signatures that it leaves in the static spectrum. So I obtained NASA funding in order to develop a technique to identify variables from archival near infrared spectra. And this will be crucial to prioritize variability targets for the James Webb Space Telescope that is already in place, which is very exciting. And this work was led by my undergrad student, Afra, who has recently submitted a lead author paper detailing the technique and has been accepted to grad school. So I'm very proud of her. And so now, after accounting for the variable false positives, we have also carefully mapped the detection biases of the spectral binary technique in more dimensions that I'm showing here, as a function of age of the star, primary and secondary mass, primary and secondary temperature. But I'm just showing here the shading in order to reinforce the idea that this is a separation independent technique. All that you care about is that the 2 stars fall within your spectrograph at the same time. And so my goal is to map all of the selection biases from all the techniques to really understand our survey completeness and determine how empty this valley really is. Now, the other problem that I had mentioned were the companion masses, which thanks to Gaia may not be a problem anymore. So the dynamical, for about 6,000 stars within 100 parsecs, the proper motion measured in Hipparcos in 1990 is different from the one measured in Gaia. Let me break this down. So proper motion is the motion of a star in the plane of the sky. It's the velocity that the star has as projected onto the plane of the sky. And Hipparcos was the predecessor of Gaia. Hipparcos was another satellite telescope that measured the distances to probably over 1 million stars. That was huge at the time. And in 1990, Hipparcos measured the proper motion of about 1 million stars, but 6,000 of those stars within our local volume, when their proper motion was measured again by Gaia in 2015, they had shifted a little, and there's no real reason why it should be any different besides instrumental uncertainty from both telescopes. The reason why it has shifted so much is because there's a hidden companion. So again, the hidden companion is tugging on the star and is making it spin like a top. And then when you combine, this is what we call a proper motion acceleration. And when you combine these accelerations with radial velocity, you can get the full architecture of the systems. Think about this as a problem where when you attack the problem in 2 different angles with 2 different sets of measurements, then you can learn so much more about the system than you would if you were just looking at just one part of this parameter space. In this case, we're combining techniques, and by doing that, we're actually getting a lot more information than we would otherwise. So this is the radial velocity curve of 14 Her. 14 Her is a star. It's a K0 star, which means that it's a little bit less massive than the sun. And we know that it has 2 planets around it because we see this regularity on the change in radial velocity. That's the first planet that is closer in. And then we also see that there's a long-term trend. And that suggests that there's a second planet that has a longer period. So we already knew about the planets. The planets were discovered in 2007. But we only had a mass from this radial velocity measurement that depended on the inclination of the orbit. Remember, the radial velocity, you're only looking at the line of sight. So you don't know if your orbit, you don't know the inclination of the orbit. You only get that component of velocity that's in your line of sight. So since all we're measuring is this change in the radial velocity, there's this factor of sign inclination that you can't shake off unless you have an independent measurement. So my REU student, Lauren, and I, we use this code called ORVARA to determine the full orbital architecture of the system. And the ORVARA code is robust and it's accessible for an undergrad to use in a short period of time. It's very user-friendly. So ORVARA, it's hard to mention, takes the radial velocity and the absolute astrometry from Gaia and Hipparcos, fits a Kepler equation that is just like fit if it's an orbit, with a sampling method that's called Markov chain Monte Carlo, or MCMC. And so MCMC, what it does is that it lets you explore a bunch of variables at the same time. Think about this like a hilly landscape. It's multidimensional. And the solutions are at the top of these mountains. So for our system, this is what we find. The B parameters were already fairly well constrained from before. What we did for the first time was disentangle the mass from the inclination. And this is thanks to the MCMC that was able to find a solution at the peak of the mountain of all the dimensions at the same time. And then the C parameters were a little bit harder to constrain because our RV data only covers a short part of the whole orbit. But we find that the B planet has a mass of about 9 Jupiter masses. The C planet has a mass of about 7 Jupiter masses. The B planet is located at almost 3 AUs from the star, which for our solar system, that would be about where the asteroid belt is. Whereas the C planet is much further away at 27 AUs, which is roughly where Neptune is. So that feels a little crowded. These planets are really massive, except that unlike our own solar system, these planets are not in the same plane. So if you take a close look at the inclinations, the B planet is at 32, the C planet is at 101 degrees inclined. Both planets are also in very eccentric orbits. This is a far departure from a circle. And these 2 pieces are very important clues in order to reconstruct their dynamical past. So based on the orbital parameters, we realized that the system looks something like this. Here we're approaching the star, and the C orbit is the one that is farther out. Sorry, that was the sun. The star is really tiny. And as you can see, the orbits are sort of crossing each other. So let's examine this crime scene. The current day orbital architecture of these planets gives us some important clues to understand the evolution. So first we'll look at the eccentricities. In general, multi-planet systems tend to have low eccentricities at formation because it's more energetically favorable. However, the high eccentricities of 14 Her are typical of multiple giant planets in a disk. that first form and then scatter each other due to mutual gravity. But the chemistry of the star is also important. The star is metal rich, which means that metal in astronomy just means anything besides anything after helium. So we call some gases are actually metal just because hydrogen is so abundant in this universe. But in systems with metal-rich stars like 14Her, the orbits of giant planets tend to be more eccentric than those around metal-poor stars. And this is a consequence of planet-planet scattering. So planet-planet scattering is when you have a few planets, all of them in a disk, and they're kind of close to each other. Their mutual gravity essentially makes them scatter. Another reason could have been that as the planets were forming in the disk still has gas, the gas has mass, and so interactions between the newborn planets and the gas could have caused some disruption of the orbits, or it could have even been a nearby flyby. So some other object that like came by relatively close, injected a little energy to the system, and then disorganized the whole orbits. Moreover, 3-body simulations also show that ejection could be a likely possibility in the early phases of formation. So it is possible that a third planet, in which case would have been the least massive one in the system, would have been ejected from the gravitational potential of the star as a consequence of these dynamical interactions, causing the final eccentricities. So if 14Her really did lose one of its planets, what would it look like today in the wild? So the ejected planet would actually be an analog to some of the coldest brown dwarfs. It would have a temperature of about 300 Kelvin and would live in this very sparsely populated part of this color magnitude diagram. This is pretty similar to an isolated object that we found recently with the Backyard Worlds citizen science collaboration. So in Backyard Worlds, people from all over the world look at these little videos. And this video that I'm showing here is a set of mid-infrared images from the WISE Space Telescope. And so citizens all over the world look at these videos to try to identify very faint, very red, very fast objects moving, which could be the coldest stars or ejected planets. And this is a critical, vastly unexplored population to understand brown dwarf versus planet formation. We've been awarded 2 programs on the James Webb Space Telescope to characterize the mid-infrared spectra of these objects and also to identify companions to them. And I worked on this project with my student. That is a good example. This object that just popped up, that is a good example of how poorly understood this population is. And I worked on this project with my student, Austin, who went from citizen scientist to full-time grad student. And he's now identifying the widest binary systems that contain brown dwarfs, similar to BD plus 60, which I showed earlier. So I'm really excited for this new era of population astronomy, where Gaia will provide astrometric binaries all over the place, accelerators and masses, and that's coming soon. And the Rubin Observatory is, with the Lsst Survey, is a ground-based survey that is going to look at the whole sky, searching for transients. So it's going to be looking at, it's going to take data of the same region of the sky over time repeatedly to see how things change in the sky. And this has the perfect cadence and the perfect sensitivity to measure the parallaxes, so the distances of really faint brown dwarfs. And this can also be a way to identify companions to those brown dwarfs. I'm also really excited for JWST, so we can characterize the atmospheres of these very cold objects, because for the first time, we will be able to look in the mid-infrared where these objects are actually brightest. We haven't yet been able to do that, which brings me to my next point. How do we identify chemical signatures of formation in the compositions of low mass companions? So let's consider the different compositional signatures of each formation mechanism. In binary star formation, each component collapses from the molecular cloud independently. So their compositions should be the same, right? They're being cooked from the same material. Whereas in planet formation in a disk, formation occurs after volatiles have evaporated from the disk. So the planets form after the star is done forming. And therefore, the companions should have a slightly higher metallicity with respect to the star. There is less gas available. Volatiles, I forgot to define. Volatiles are essentially gases that can evaporate at low temperatures. So then when you're forming your planet, you just don't have that much gas available. And in fact, and so the way in which we're going to try to understand the compositions of these companions is by using their spectra. So, well, an image is worth 1,000 words. A spectrum is worth 1,000 images. The spectrum of an object is a unique fingerprint of its composition. And here I'm showing a spectrum of a brown dwarf, just as an example. On the x-axis, we have wavelength in the near infrared. And then on the y-axis, we have a very complicated way of saying flux. This is just light, like intensity of light. Traditionally, we use something called forward models to model a spectrum, which means that we have entered, which assumes that we understand how the atmosphere works, and we just make a model of it from first principles. But there are lots of things we don't understand about these very cold atmospheres. We don't understand the convection in the atmosphere, how material gets dredged up from the bottom into the top, and the top is what we can see from the spectrum. We don't fully understand the opacities, so how opaque each one of the elements and compounds and even clouds are in the atmosphere. We don't understand the weather processes. There can be this equilibrium chemistry, cloud patchiness, all sorts of problems that we don't fully understand physically yet. So it's very hard to model. It's very hard to model an atmosphere when you don't know what's going on. So the state of the art is now to take a data-driven approach that's called retrievals, where we provide a spectrum here. This is our observation. We provide a spectrum to this black box, the retrieval algorithm, and we give it priors. So that means that we tell it, we give it priors of what we think are the most probable distributions for each one of the parameters that we're trying to fit. And then the retrieval algorithm does this MCMC that I explained, or more advanced sampling methods. MCMC is actually falling out of fashion now, but it explores this landscape and tries to find the perfect place where all of the parameters are most likely at the same time. And it reaches this best fit model, and it provides the posterior distribution that is just a fancy word for saying the answer as a distribution, not as a unique point. So this is a probabilistic way in which we can understand the compositions of brown dwarfs. So I am using Brewster. It's this retrieval code that can handle cloudy atmospheres. It's the only one that can handle cloudy atmospheres. And I'm using it currently to obtain the composition of a companion to a pair of red dwarfs. And again, because the idea is to use these systems where you know the composition of one, and we're just trying to find the composition of the other and then compare. These are very complicated plots that I won't have time to explore in detail, but what they indicate with Brewster is that we can obtain the composition of gases, the composition of the clouds through Brewster. We can obtain the vertical structure of the atmosphere. This is again a very complicated plot, but in the y-axis is the pressure. So you can think of going from top to bottom as looking deeper and deeper in the atmosphere. For example, the code has told me that here where this purple block is, that's where a cloud should sit. And I'm taking this approach to compare compositions and metallicities of the host and the companion to determine the formation pathway of the secondary. And this is the fit that I've obtained with this code. And so here, the black line that you can barely see that's behind is our data, and in green is the maximum likelihood of our data. So in green is essentially our fit, and I am pretty pleased with this fit. So I'm very excited to finally appear in the mid-infrared where brown dwarfs are brightest with JWST. And I'm really excited this is all going well. That is an actual image of JWST finally in its location in the second Lagrange point. So I'm really excited to see that everything's going well. And then quickly to go back over the best formation pathway targets to use this technique. The best ones are benchmark systems, as I mentioned, where we know the composition of a star and we're obtaining the composition of the secondary, and then we can compare between the two in order to understand whether it has a higher or lower metallicity to see if it formed as a planet from a disk or if it formed from the same molecular cloud as the star. But also, it's important to look at chemically homogeneous populations. And this is work that's been led by my student, Lsst Gonzalez Quevedo, who's also Peruvian, and she's in Peru right now. And what she's doing is she's exploring the AB Doradus young moving group. What that means is that when stars are born, they're born together from this molecular cloud, and they evolve together. And through their kinematics, we can understand that they're still moving together when they're fairly young. So she has grabbed this population and she's identifying their rotation rates using Likers from TESS. TESS is a space telescope as well. And TESS is monitoring the whole sky in order to obtain changes of flux over time. So, and that tells us how quickly stars rotate. And the way she's doing this is that she is, in the end, constraining which stars really belong to this group and which stars don't. And therefore, we can tighten our chemically homogeneous population. So this is also like an avenue for future student projects. Retrievals are a great way for students to get a handle on computational projects and increase their coding abilities. TESS is free data, so we can also work with students from all over the world, like Lee said. And it's important to teach this method of skills, I think, so they can be used in other countries that don't necessarily have startup money. And I'll talk about that a little bit towards the end. But sort of to close off this idea of the chemical and dynamical signatures, what I want to do next is to do a volume limited survey of dynamics and chemistry. So I will use Orbera on the solar neighborhood in order to get masses for about 250 systems that have that both have radial velocity and astrometric accelerations, so that we can obtain masses. And that can be done essentially right away. I don't need new observations for this. And then I will also use Brewster to get the compositions for all the benchmark systems within 25 parsecs and understand the composition of the secondary. As we're doing this, this is a field currently in astronomy where observations are driving the theory. So why not use observations to build the theory? My goal is to identify the orbital parameters that, many parameters at the same time, so we can build a multidimensional probabilistic model of formation, similar to the MCMC sampling that I have shown before. Try to find what is the most likely way in which any of these companions formed using these dynamical indicators. And then when JWST starts taking data, we can start looking at spectroscopic signatures of formation. So look at the spectrum of objects that we think are forming in different ways and try to identify markers that can separate one from the other. And specifically, we already have some ideas of what this could be. It could be water that has one deuterium atom instead of a hydrogen, or also methane in the same way, deuterated methane. It could be the ratio of abundances between carbon-13 and carbon-12. So we have already some ideas of what could be. We just need the data, and then we'll get going. And I also want to, since we're going to be calculating compositions anyway, then we can do galactic archaeology with brown dwarfs. So what this means is that this is a picture from the dome at the Hayden Planetarium where I work. And when Gaia came out, we went to the planetarium and we color-coded every star based on this main abundance. So I think here, yellow and green is solar and slightly supersolar compositions. Purple and blue are iron poor compositions. But now imagine this with brown dwarfs and giant planets. So there's about one brown dwarf for every 5 stars. And this would the nice thing about brown dwarfs is that they don't fuse any hydrogen. So their compositions are pristine from the cloud that forms. So essentially this is a picture of today's compositions, but with brown dwarfs, you could get a picture of the composition of the past. So in that way, we can start tracing back how our galaxy evolved with brown dwarfs and giant planets as well as stars. And since I mentioned Lsst, one quick thing I wanted to mention as well before I finish my talk is that I met her through a program called Cosmonautas. I led this program with another postdoc, also from Peru. She works in Germany, and Cosmonautas is a workshop. It's a project that is running again this year. What we did was we offered a teacher training workshop for teachers in rural areas of Peru. Amauta is the Quechua word for teacher. And we reached about 50 teachers in the last run. We created this book that you can check out here. Of course, it's in Spanish, but we created these resources in Spanish and trying to develop international collaboration opportunities and increase the accessibility and representation in science of countries that don't necessarily have that much scientific community yet. And Lsst is a great example of this collaboration. So just a few points to finish my talk that I want you to remember when you leave today is that with dynamics and with chemistry together, we can tell the story of formation of all of these planets and brown dwarfs. And then with the existing Gaia and the upcoming JWST, LSST, the Roman Space Telescope, and all of these upcoming facilities, I'm really excited about all of them because we can finally characterize all the neighborhood systems and study them statistically. And with these surveys, we'll be able to build a comprehensive theory of companion formation that's anchored in observations and identify spectroscopic signatures of formation as well. So with that, I'll take any questions, and thank you so much for your attention.
Thank you very much. It was really impressive, and the visuals were really pretty, and it was very detailed and informative. We have some questions, and I'm asking from the audience if they have any questions, they can write in the chat box. So we have a question from Madiha. So she's asking, what are the struggles, faces, studying and making conclusions in terms of technical aspects as well as resources to carry out the studies? What is the long-term goal?
Interesting. So let me see if I understood the question. So what is the long-term goal of this piece of research, and how do I get to conclusions? Like, how do I know that I'm in the right track at the end, I guess? Okay. So I think that every scientist will have a different question for what you think is the big thing, right? But what I think is the big thing is understand information. Eventually, we want to find planets that are habitable, planets that are like the Earth, or on stars that are like the sun. And our instruments are still kind of at the edge of what that could be. So we're getting there, but we're inching there. And I'm excited about my research because in this way I can provide a global view of how anything can form in the universe, not anything, but like stars and planets and brown dwarfs. And then we can also specify which conditions are best to look for life later on. Imagine that that certain planets around certain stars just don't have the conditions because of temperature, because of the chemical composition of the planet. If there was no oxygen, then possible, which would be impossible, but if there was no oxygen, for example, then like we couldn't try to find life that looks like ours necessarily, or any other bacteria that breathes oxygen. So there are some differences. There are some places that will be better to look for life than others. And what I'm hoping to do with my research is to provide sort of the ground truth first. And then when you find anything that deviates from that, then you know that you have something interesting. And how do I know that from technical conclusions? I think MCMC is a great example of that. You never actually know that you've gotten to the right answer. You do a lot of tests, you test convergence. So essentially, if you run your experiment 10 times and you're always getting the same answer, then you're fairly confident that you have the right answer. But of course, there's a tiny little probability that you're completely wrong. And that's just science.
Thank you. We have another question from the audience. Javeria is asking, it's a technical question. What are the retrieval algorithms based on? Physical principles or machine learning techniques or empirical data?
That's a really good point. It's based on empirical data. Let me go back to the slide that shows the retrieval algorithm. Right. It's based on Bayes' theorem. So Bayes' theorem, what it says is that it was a big departure in statistics because it was no longer like the universe is not deterministic and we know the answer for sure. This is more like we'll have some probability that this is how things go. So at the heart of this is Bayes' theorem. And so what you do is essentially, in the simple case of retrieval, you have, again, imagine this landscape where that has a bunch of dimensions, more than we can imagine as a landscape, and you let go these walkers, and the walkers essentially like take a step forward and say, okay, is this a higher probability state than where I was before? Yes, great, then I keep going in this direction. If not, then I go back and I go somewhere else. And so you have like hundreds of these things running all over the idea is to span your whole landscape until you find a place that is more probable than others. And that's how the retrieval algorithm works. So essentially you're taking a spectrum and saying on each piece of the spectrum, what if I have this mix of gases at these levels of abundances? Is this more probable than the last mix of gases that I tried? Does that answer the question?
Thank you very much. Okay, so we have Dr. Fawzia Parveen with us. She is part of LUMS faculty and she really cares about the environment. She is also offering courses on it at LUMS. So she has two questions. One is, could you tell us a little more about the stars having their own light? Does it have to do with the composition and how is it characterized since they are so distant?
How do stars make their own light? Is essentially through this process. So it doesn't have to, okay. So for stars to just make light, it doesn't have to do with the composition. Most stars, all stars are mostly composed of hydrogen. This is why at some point I said like metals in astronomy are the whole periodic table, except for hydrogen and helium, that like chemists will differ. And so in order to just like produce any sort of light, all you gotta do is have the conditions in the core necessary to ignite and sustain hydrogen fusion. But the type of light that you produce will be different dependent on the total mass of the object. It still doesn't depend on the composition. So so the like more massive stars will be, because they're so massive, gravity is so much stronger than in a low mass star, then they need to be cranking up these nuclear reactions a lot faster than they would in a low mass star. And that makes them, they're much more energetic, and then that releases photons that are more energetic as well. The other thing that I'm thinking is that, well, yeah, so I mean, more massive stars will produce more energetic light. So this is why stars can be blue or white or red. And the stars that are red are actually colder and they emit light in red wavelengths, which carry less energy than the stars in blue wavelengths. The question with composition is interesting, and stars do have very different compositions, but at such a small level that it's not crucial for them to make light in different ways based on the composition. Yeah, and there's one more thing I want to say about this, but I'm forgetting.
Okay, thank you.
Yeah.
She has another question. Since I just said that she really cares about the environment, so she says that I have also recently been fixated on the idea of space debris. I want to ask what I asked recently. Is it something we should be worried about?
Space debris. There's a lot of debris in the universe. There's debris that naturally is there because, I mean, you could think of debris in disks around stars, and then planets will form. That happens, of course. Disks, there are some debris disks, actually, that's what they're called, around stars that are a little bit older than the protoplanetary disks, and those are also made of, like, rock and dust and everything. Then there's around the Earth that has a lot of satellites and space junk and things like that, and, like, cars and Elon Musk, like, orbiting around. So that is concerning. For sure. I think that I am no expert in space politics and policy, but it's still not unlimited. And if you want, I mean, we have all of these satellites around the Earth that are necessary for our cell phones to work, for us to be having this phone call, and at some point that will be very crowded. So collisions are common between, satellites and rocks and meteorites and everything that could, like, tamper with our telecommunications and stuff like that. And yeah, and don't get me started with Starlink.
Interferes with your work as well. I mean, these are one of the things that, yeah. So what we call in economics, these are, I lost that word. So limitations, yeah, limitations.
Yeah. Mm-hmm.
Okay. Okay, now I have a question that just came to me. Yeah, sorry.
So you can go ahead and ask your question, but just so we know, we're above time and we are losing people, and we don't want to keep the speaker here for too long. And obviously, I have questions and I have no time anymore. But
okay. Thank you very much. I think that's it. You just
go ahead and ask your question. That's fine.
Okay. So you were just talking about the star binary system, and you proposed two basically concepts: radial velocity and astrometry.
Mm-hmm.
Are these basically extensions of Newton's fourth law of gravitation? Because from that's basically a bigger concept to study how two objects remain in the orbits, and they are basically attracting each other according to their velocity and mass. So yeah, it's a bit technical. Yeah, so that's my.
Yeah, no, you're completely right. I mean, the reason why we can make these observations is because of gravity. So gravity, we don't necessarily see the component. These are all indirect methods of identifying companions because we don't see the companion itself, whereas direct imaging is a direct method. And yes, and the only difference between astrometry and radial velocity is what data you're using to identify the companion, because they're both they're both looking at the same phenomenon. You have a star that's bright and you have a companion that's faint. And the companion is orbiting around the star, but they're actually orbiting their common center of mass, not just the center of the star. So then the star wobbles a little. And the sun wobbles a little too. It's mostly from Jupiter, not from us. But all stars will wobble, and they won't actually stay in the exact same place if they have a companion. And so in radial velocity, what you see is that as the star is wobbling, it's going to move like a little bit towards you and a little bit far away from you, and then comes back and then does this motion. And with radial velocity, all you do is detect that radial motion. You don't see anything from the sides. What you're getting is a spectrum, and then a spectrum like 6 months later, and a spectrum 6 months later. And when you're like cleaning up your data, essentially, you realize that spectrum, what you do is the spectrum has a bunch of lines that are from certain elements in the star. You try to match them with lines here from our labs on Earth, from chemistry labs. And so you know that, for example, whenever you see this line, it is showing up at this wavelength but on Earth, it shows up at this wavelength, and then you correct them with velocity. And this is how you measure the velocity like that comes towards you and away from you. If you're working on astrometry, you don't use spectra at all. What you do is you take images and then very precisely measure the center of light of your star that is not actually the same as the center of the star sometimes. And that's because you are getting the light from both. So so imagine that you have the light from the star and then the light from the companion that's so faint that your telescope sees them as one big blob, not two. And even if it's faint, it's still emitting light. And so the center of light won't match the center of your star in the image. And then when you measure this like over time, you see how like the little center of light has a tiny little orbit, and that's how you identify astrometry. And this is really hard to do, which is why only like 3 companions are known that way. Low mass companions, I should say. We know of a lot of stars that have companions through astrometry, but the brown dwarf and giant planet companions are essentially none.
Okay, so I'll take it from here. Thank you so much, Dr. Gagliuffi. This was an extremely interesting seminar, probably my favorite.
So
Although there were so many things that I did not understand because it's obviously not my field, but it was still so interesting. And already we had a few emails asking that, if we can get the recording afterwards because people eventually had to leave.
Good.
But thank you so much for coming before time, and now we're making you leave after time. And this Dr. Javeria, who also does, we don't do this at all. That's way out of our league. But so she said, hope the James Webb Telescope advances your work by light years. And considering she's super smart, this is a pun, has to be. So yeah, that was very sweet of her. I thought that I should say that. But thank you so much. It was lovely. And we'll let you go from here. I'll obviously send an email with some follow-up answers, with questions, and it's totally optional for you to respond. But thank you so much. It was extremely interesting. Best of luck for your seminar tomorrow with the students.
Okay, thank you.
Thank you so
much again.
Thank you.
Great to be here.
Bye.
Thank you. Bye.